Well, good morning, everyone. After Nishant's perfect technical presentation, I'll be talking about the vision that why we built, a national supercomputer, and what's new about building a supercomputer in Denmark, and why for life sciences, because we believe this is something very unique we have done. And
let's move the mic to here, so that way it's rubbing up against it. All right. A little bit.
Perfect. Great. So my name is, as you know, is Ali, and I've been into the team or managed the team who built this supercomputer in Denmark. So let's look at the history of Denmark. Denmark is a very unique country, at least we think so. It has 2% of GDP related to life sciences, which is basically we have large pharmaceuticals. Unlike to US, they are foundational based. And there is a big tradition about public and private partnerships. That's a very unique eco-structure as compared to the rest of the world, which meant is that we have a lot of users who are researching for these large pharmaceuticals. And then 20 years ago, we went in and developed a strategy for HPC like everybody else, and it kind of really failed. And I'll explain why it failed. What happened was that data is becoming more and more cheaper and available. We are mixing data from different sources. Now we have Apple Watch. People are walking around with personalized devices and sending that data into the healthcare system. When we started, the data was from the doctor's notes. We implemented doctor's notes about in 60s, which meant that we have a lot of history about Danish population. What we also did about 20 years ago, which was very nice, was that we went out for an opt-out model, that if you do not want your data to be used in research, you have to actively go out and say, no, I don't want to do that. And we all know that 99% of us don't do that. So we ended up with massive amounts of data, and we did not know what to do with it until last couple of years. And then on top of it, because of our financial system, taxation authority and everything, we had a lot of lifestyle data on people available as well. And then we started with an effort of sequencing people, because that technology is getting cheaper and cheaper, and the byproduct of that is that you get a lot of data. So the first problem is we baselined that data. We have a lot of data, and we did not really know until a couple of years what to do with it. Second part is, as I said earlier, is that we have a very big community. And the word, bioinformatics is pretty small, but if you look deeper into it, there is a lot of disciplines, and just like high energy physics and others, people do have different requirements, and they do not like to work with each other. So just to name a few ones, proteomics and genomics, and you name it. With the pictures, I'm just trying to illustrate that from the science part, they're different, but from the compute part, which we all are interested, they are very different. So, for example, each omics has a different compute profile. Some are very related to a very fast processor in life sciences, and some do not care about a fast processor, but they need a lot of I/O. So it's really difficult that you have multiple types of data, multiple types of disciplines, and you're trying to design a system which is perfectly balanced. Do you go for fast CPUs? Do you go for fast storage? Or do you go for fast everything? And then you run out of money. And this is causing a lot of strain on the existing systems. They were not designed to handle that much amount of data. I can give you an example, is that we every year generate around 2 to 3 petabytes of data locally ourselves. And that data needs to be backed up, shared, and it's a nightmare. A lot of people call it as an omics onslaught, fancy word for it, but this is a real problem. But just to, set the scene and tell you, in Denmark, we have started to sequence our population, which a lot of countries are already doing that. That's a big problem because technology is cheap, and that means you can sequence a lot more. We are under $1,000 genome, and it generates about 400 plus terabytes, depending on which type of sequencing you do, to a few terabytes per person per time. And that's a lot of data. To make life even worse, that our friends in the US, thanks to Mr. Obama, created this personalized medicine initiative that put a lot of pressure in the European authorities. Lawmakers are now interested in doing the same for their population. We have an aging population in Europe, and we need to give them, we need to, on the one hand, save cost, provide better treatment. On the same time, we need to give them a better quality of life, and it's a very difficult equation to balance. And to be honest, if you look at it, a lot of times when you're treating people in the hospitals, we are causing a lot of grief and pain by administrating different types of drugs. We give them different, what version of penicillin doctor remembers. Maybe that patient needs less, maybe he needs more, and then they give him multiple medicines, and then, you make a mess. As, Nishant was also saying that in his calculation, they were looking at one drug. Look at a patient usually gets 15 different drugs in an ER and get mistreated. And these things can be done very, very easily on a computer. It's not, difficult with the technology where we are. So by looking at this thing, you have a lot of data, you have a lot of challenges, but this can be done. So in Denmark, we, just like everybody else, created a big, you can say, group that went out and started doing a study. What we did was that we went out and looked into our basement. What do we have? As you all know, in an academic environment or semi-academic environment, every time you got money, you went out and bought the next, biggest and flashy storage system. We did the same. We had a lot of it. Not very proud of it, but we had to do it. Then we realized that this is an environment which is developing. Applications usually remain from 3 to 6 months, and then something latest and greatest comes in, and we add it into our tools. And this latest and greatest needs some time to be distributed as well. So our portfolio is growing huge. We have a search engine like Google, where you can go in and search applications, and it has around 6,000 today. So that shows you 6,000 applications that needs to run on a computer, which was not really designed for it. Number of jobs, as you all know, this is research as well. So people are doing tests. They run something and then they get some output and they really don't like it, and then they run, the new thing again with multiple flags, 50 different times, and you end up having a very big overloaded system. And then the profiles. We had people from doctors to bioinformaticians, postdocs. We love them, student helpers. Everybody has to run on to the system. So basically, we had something which is more like a Wild West. It was rebooting every time, and you need to send emails and saying, people clean up, otherwise we'll do it for you. And I think the base problem which it was giving us was the policy. Because you're sequencing and you're getting personal sensitive data into a system which was not really designed for it, how do you back it up? Lawmakers are behind you. Your own management is behind you and asking you back it up. Then you back it up, and then say back it up again. And who has access to it? So it wasn't really working, as you can see. And just to emphasize this point again, this was really killing us. People were making applications every single day, and 90% of them were made by people who shouldn't be programming, but they were programming. Yeah, please don't quote me on it. So, well, I can hear some people recognize it. But anyways, it was a Wild West, and badly written code was one of our biggest problems. So what we did was that we went out and did a reference architecture. What we realized in our 20 years of research is that storage is great, and you can buy the biggest storage you can, but it's not more about the size of it. It's throughput, how much you can, shit in and shit out. Some people say it. Again, compute, latest and greatest CPUs, GPUs are great, but at this stage, we are looking at scalability. When you have a patient in a hospital, he's not worried about how fast your CPUs is. It's about scalability, and can you feed that CPU that it's running 100% and it's not idling. Next part is access control. Traditional access control happens on the users. You have your VIP users, and then you have users. What we realized that people were getting tired of it. We need to have groups who can access this data because data is too big. And also user-defined environments, because it's a very new environment, so you need to allow users flexibility to define what they want. You give them something which is stable enough, and they can, go in and develop and work with the system, not against the system. So that's always a better strategy. The last part is integration. Because of our unique eco-structure, we had industry and hospitals, and as you know, all traditionally they don't like each other. So we had to be this glue, historically, that should come in and push these types of innovations on each other and put them on a single table.
When did you come up with this? So you're talking about this year, last year? Or
it was last year, yes.
Okay.
So things have changed. So, and also the part is that you need to make relevant data accessible. We are still fighting with it, but I can show you what we have done. So what we did was that we went back to government, and they were happy enough to give us a lot of money to buy a supercomputer, which is 121 place on top 500, and we're really proud of it. But the idea was that we built a reference architecture for the whole country, and we managed to convince most of the universities that instead of building into a basement, let's put something together and do it the right way. So we went out and found a new site, which is a greenfield, because we did not really like the brownfield, retrofitting the brownfield. We tried to build a system which can be used by others than life sciences, but mostly it's dedicated to life sciences, and there's a lot of memory in that system, around 92 terabytes in total. But the focus is more on the I/O, as you can see, and the storage part of it, we bought the system that can move some data around. That was our biggest challenge. We did not go for a lot of GPUs and similar technologies, and primarily because of our applications are very new. We do not get the chance or possibility to tweak them because a new one comes in right after. It's just it's not possible. Of course, we are looking at it, those types of technologies, but we rather invest in faster interconnect and things like that, which helps us move the data, than on faster compute cycles, because the business case is not there so far. To house the supercomputer, we opted out not to use our basement, so we went for the containerized system. We developed specific containers that can house these systems, because we know that turnaround time on this technology will be, very quick, and after 3 years it will be too old. So we wanted a complete modular system. So we started with buying a lot of power in Denmark, which was a nightmare in itself, but we managed to build, you can say, highly efficient containers built for the Danish environment and not for a combat area. Then we looked into scalability part, because we realized that if we have to connect hospitals and the old population, we need to scale the system, because once this goes mainstream, we cannot wait 1 year to get a new system implemented. Secondly, we provided redundancy because of the SLA we had on both ends. And the third part is that the supercomputers these days, especially in Denmark, we saw on Nordics, we have a very good climate. But people are moving those systems to places where, energy is cheaper, or, climates. We realized that we can use technologies in the market that can allow us to reuse the heat, or, reuse the resources to get a better business case and to be environmental friendly. That I will touch upon in a minute, but primarily we have a system that can discharge about 1 megawatts of heat into the district heating system. So when we started, we were given a place which was kind of worse than the basement. It's a site which we owned. It's right next to solar cell, and there is some wind turbines down here and a lot of water. But the site is pretty much, a junkyard. So we started, transforming this place, and started, connecting those solar cells, and we have the district heating facility right next to it where we can discharge it. And we are also using some solar power. It goes into the grid and back again. So from that perspective, it's very green. So after cleaning up and everything, it looks like this. It's fully, scalable, flexible architecture. The power is coming here, and you can add more transformer as you go along. And yeah, these are two small 50 feet containers. They look very small on the picture, but they are slightly bigger. So that's what we did. And that's actually very, great. Now you have a very big supercomputer, and it's now going to be running and doing a lot of good stuff. But how do we leverage this, Having one supercomputer, a very complex environment, and, a lot of things, in there. But how can we give this to a doctor that he can go in and press a button and supercomputer, works for him? That was a very big challenge. And actually we realized this later on, once we were building this, that only a handful of people in the nation will be able to use it, the top researchers. But that was not the point. So we needed a vehicle who can go out and automate a lot of the work. So, like everybody else, we found out our idea of using a cloud. A cloud is great in many aspects. It can do a lot of things. But what we realized we wanted cloud to do was very, very simple. We realized that data is going to be bigger and bigger, as I said earlier, sequencing and everything. And we realized that since it's a developing area, which means applications will, come and go very quickly. How can we change this? So basically, our business case is built on cloud, is on two different things. The first one is that in traditional way, when you find something, some smart guy finds something, he creates a script, and then his buddies get it, and then, you cascade it down to the doctors or people. By the time it ends at the mainstream, it's too late. The results are not accurate. So we realized that we should do a cloud front end that takes care of security and all those methods, and it can be deployed quickly. It's like, I heard yesterday, like Google Chrome does it, that you do not have a version on Google Chrome, they automatically update it. So we are looking into a system, or we are doing a similar system, where we automatically update the application in the backend. A new algorithm comes in, great, we update it. But for the doctors or clinicians, the interface remains the same. And the researchers get their favorite, interface they like to do. So that was one of our, you can say, our biggest pain we could solve this way. The second thing we realized is that since we are working cross EU or US, data, for example, those people who are familiar with life sciences, is generated everywhere. For example, one of our biggest partners is BGI, which is generating it in China. And they are shipping us disks through trucks. And that's great, but somebody has to take it, install it, and transfer it, and it's a painful process, and it's not a sustainable model. So what we realize is that in our concept, and since in the spirit of everybody is doing clouds, the way we envision, or when we talk to our partners, we convince them to cloud burst into each other. So if we have to do an analysis in this red place, the tools are sent there, and that analysis is happening there, and then we come back and then work on the data that we have local. So we do not ship our personal data. And this was enforced by the fact as well that Europe is, multiple countries. It's not like continental US. We are not allowed to send our data cross borders. So this is the only way we can solve this challenge. So these are the two things that we are trying to, solve with the cloud. And trying to get a bit higher utilization. What we have seen in this, yeah?
Sorry, how we solve the problem with data? I don't understand that.
So basically, let's say if you have data that is being generated through a sequence or whatever, and it has to run, then we actually send the workflow, the applications that are going to analyze to, for example, China. They go down there and they query the data. There are multiple layers. Sometimes you do give access to data, sometimes you don't. And then it queries that interface and get the result, which is typically very small. And then it comes back and executes the rest of the, you can say, workflow or pipeline down in our basement. And then, move along. So because of having a lot of types of data. We have people's lifestyle data, which is not with us, it's with another authority. So we actually burst into their cloud. Traditionally, we used to give them a server, and they used to house our servers with, we managing it and they managing it. Now we actually log into their interface where we are exposed to this data set through a query-based system, and we query it and come back.
You send the application package somehow to them?
Yes.
And then you get the intermediate information back, or you only get the result, or you don't get anything?
It's case by case, but typically it's intermediate results you get back. And then you run further on your pipeline, because typically in life sciences you run a pipeline.
Since it's an intermediate result, you cannot check out the information of the person?
Yes. It's aggregated somehow, exactly, because data is, huge. A good example is on rare diseases. Rare diseases is something that happens to, 1 in 200 people or more in some cases. So that's something you cannot do in Denmark. We are about 6 million people. So that type of analysis has to run across EU. So these are EU initiatives, and where you basically go into different countries and, query that data and come back. So that's a you can say a good example for that.
How do you ship this application?
I'm going to come to that in a minute. You're too fast. So basically, the first step, our first mandate was that, bridge healthcare and industry. Industry, as you know, is in need of these types of data back. They are developing medicine which was developed in, the old way, as my colleague earlier described, that you go out and you test in different types of people, different nations in the last part of the testing. But what we believe is that the testing should happen on a personalized genomics base, how people are built. You need to look at the structure of people. We can be very different from each other, even though some of us look alike. And the second part is, what we are trying to do is that we are doing collaborative research on sensitive data. This is where the holy grail is. This data has been kept so long time, isolated from research, and this can really, change the way we develop and work. The third part is we have created a collaboration with us and a hospital and a pharma company to go out and implement this in two you can say use cases. One is with mental diseases, and the other is with insulin-based research. Some of the use cases we have done, we have been up with this type of technology for last, 8 months. And one is this Trygve, where we have created, you can say, a consortium of Nordic countries, which is Denmark, Norway, Sweden, and Finland. And we are sharing our sensitive data. We have written certain framework which allows us to share this information between us. Next thing we've done is we have implemented the embassy cloud service. That is answers to part of what you said. This was developed by EBI, which is a virtualized based technology where you send your workflow to the other location, like an embassy where you control what's inside and they provide resources. That's one way of doing it. We have modified it to something called islands based on Dockers, and when new things come in, we also try to push it in. And the third thing is, which is, we have used IBM Watson Explorer analytical technologies like cognitive and non-cognitive in there, because the data is so massive, you cannot really mine it. So we use similar technologies who can go in and at least tell us where to look at, and then we start looking. And they, do automatic pattern detection into the data. And one of the key use cases we have done is that it mines our data, basically patient journals, and try to find out the adverse drug reactions, that if a patient was given these two medicine and he became, bad, or he was dizzy, then we look for this word dizzy through this and find that information, match it through the drug codes, and then push it back to the industry so they can actually update their big list that become bigger, that you shouldn't take these and these things together, and then educate doctors. It's a big thing. We are trying to get the results out, but it's a long journey. So just in closing, our vision is that when we started, we saw everybody, was doing infrastructure as a service. You can ask all our tier vendors; they love that term. And then we realized some of them who had some ambition went out and started doing platform as a service. And we realized that this is also going to be saturated. So we looked into, the real visionary people, and they were saying about analysis as a service. But what we realized that doing this is great, but you always have a bottleneck, and sometimes there is a bottleneck is humans, and we try to avoid that bottleneck by try to move into this, Lifescience as a service, where we're trying to automate as much as possible. It's like your blood test. When you order it, it should execute that pipeline or whatever automatically. So that being said, that's all what I had. I'm a bit quick on this one. I have one backup slide from one of the projects we have done, where we have taken patient data, and then we have taken the genome sequencing, and you can see when you talk about patient data, it's not just one what is doctor writing. It's a lot of other things: diabetes register, death, where we register what was the cause of death register. You take birth registers, and by taking all of this data, one of the easiest calculations we do is people's trajectory. Using all this data, which is 50 years old data based on patients, we can, looking at people's biological build-up, tell how is their life trajectory. Diseases do not come by coincidence. There is always a reason behind it. And then we correlate it with their financial data, what type of, group they are living in, what type of exercise or lifestyle they do it. It creates a big, ethical question that we are still struggling with it. But it can generate a lot of hypotheses about people, which you can do and change. You can exercise more, drink less coffee, and things like that. Those things, computing can come in and change today. Combining it with data from, for example, Apple Watch or Fitbit or whatever would really make sense. This is something that can really change people's life. So, questions?
You have petabytes of data. What kind of file systems are you using, and what kind of access?
It's a very good question, and it's like a can of worm. So for the previous generation, we had 12 different file systems. We bought everything. So this time, we have standardized on EMC's Isilon. It's 1FS. Again, based on what we realized, that we were looking for a file system which was mature enough and had enterprise features for the our community, which is big part of our community is researchers and doctors. Researchers are the ones that abuse the file system, and we needed a file system that says stop. And then we needed something for the doctors that they can really work with it. So we went out for this one, and we were looking heavily on a storage system which was storage system and software solutions built together, not storage system and then put tools on top and gaffer tape it. It's like building a car and then think, oh, where should we put the driver, once it's all built and designed. So EMC was one of the companies that came up with the software tools that can allow us to manage this big jungle. It's that was one of it. That being said, we have looked into other file systems. There are a lot of them are under development, which we see a lot of potential in, because we realize we will not be able to standardize on one of it. We will need at least one or two different file systems based on the research we are using. If we need more throughput, or more low-level features, we might end up picking up something else.